when we examine series circuit like what we have here, we determine that the current that flows in a series circuit was the same everywhere, no matter how big it appears in the circuit. So whereas the voltage across the series elements were typically different. So then we introduce what we know as a voltage divider rule. So if you recall, this is what we use then. So we introduce what we know as a voltage divider rules. So when we talk about potentiometer, the application of potentiometer in voltage divider rule, how we can determine the voltage in a particular circuit, series circuit, and how we can determine voltage for a series circuit. So that is all on series circuit. So according to what we did then. So this time around, we are looking at what we know as a current divider rule, which is only applicable to a parallel circuit. So, which means in parallel networks or circuit, the voltage across uh, all parallel elements, like what we have here, uh like what we have here, the voltage across all parallel elements, like this, is always the same. However, the current through the various elements are typically different. So, which is like a reverse or a vice versa or opposite to what we have in a series circuit. So, the current divider rule is always used or to determine current entering each entry the node of each of this parallel branch. So, uh, to determine the current entering each node of this of various parallel resistors. So that is what current divider rule is meant for. So we say what current divider rule is used to determine the current, because in a parallel circuit the current here is different, while the voltage across each of these resistors in a parallel circuit are the same. So the current is different. So for us to find the current that enter the node of each resistor, we are going to make use of what we know as a current divider rule. So if this network of resistors is supplied by a voltage source, then the total current in the circuit is going to be IT, which is the total current, is going to be the voltage source over, excuse me, RT. So this is actually talking about the current that came out from the source. So that is the formula for it. Now we are going to be talking about the current that enter each node of these resistors. Now, since each of the number of parallel resistors has the same voltage E, so we said the same voltage flows through all of these parallel resistors, so across its terminal. So it means that the current through any resistor is the same as given uh, as I S equals E, which is the same voltage that pass through everything over Rx. So that is the current across each resistor. But if we can recall, according to Ohm's law, we were made to understand that this particular E, which is the total E that is common to these all resistors, is still the same thing as IR, or we can in this case say IT RT. So let's say this one is equation 1. So by the time, let's just substitute by substitution of E into equation 1. So if you put E into to replace, if you put this value to replace E in the equation, we are going to have Ix equal to IT over Rx. So you can even have the two to be over R, it doesn't matter. So that is what we are going to have. So And alternatively, if we are going to relate it to conductance, of course we know that conductance is the inverse of resistance. So we are going to have our Ix equals to Gx uh, over Gt. Please don't forget our I is also part is there, theta I. So this is always equivalent to this. We can call this one equation 2 and this one equation 3. So let's not be mistaken with this law with VDR. The current divider rule, according to what we have here, allows us to calculate the current in any resistor of a parallel circuit or network if we know the total current, which is the IT, that enter the network from the start. So to notice the similarity between voltage divider rule, which has to do with series circuit only, or series circuit component only, and the current divider rule has to do with parallel component only. So that is the we should take note of that. That the VDR, which is voltage divider rule, deals with series circuits, while CDR, sorry, I didn't even put it. You can also have it as CDR as well. CDR deals with what? A parallel component only. So we should just have that at the back of our mind. So if you are having any parallel um, problems, we should know that, and we are going to calculate the current. We should know that we are making use of CDR. Let's start from the easiest. So before we get to a large circuit like this now, let's say we have a circuit that contains just two number of parallel resistors, like what we have here. So in that case, our RT, our RT can be expressed as a R1 R2 multiplied by R2 over R1 plus R2. So I think that is the easiest way of saying 1 over RT uh, equals 1 over R1 plus R2. So I think you see the same thing to find the total resistance in a just two parallel resistor circuit. So I think it's short to say this. So if you still revise all this, you're still going to have the same thing. So now, if this is the RT, which is the total resistance in two parallel circuits, so let's just substitute this RT into our former equation here, which is our equation 1 here. So remember we said our is equivalent to IT RT. So which means if we use this to replace this in this our new resistance circuit now, which is two parallel circuits. So we are going to have our RT. Sorry, we are going to have what you call it. Let's quickly record the equation, which is excuse me, sorry for canceling this. We have I x equals IT, which is the first one we have here. So and RT is going to be what we are going to have here, which is what R1 R2 over R1 plus R2. So over what everything now is going to be all over everything is going to be all over our Rx, which is the value of a resistor which is unknown we are looking for. So let's say instead of using Rs and IL, let's say we are looking for a current that flows through through the first node of the first resistor. So let's call it I1. So we should just go through the point. So we're going to have R1 here. That is the current we are looking for. So now you will agree with me from this stage that we are going to have the next thing we are going to have from here is going to be I1 equals to um, IT, the total I, then R1, R2 over R1, R1 plus R2. So if you do your change of formula very well, you know it's still the same thing from here. So I believe R1 we cancel R1 from this up to. So finally, we can say that. So let's quickly take this. Sorry. So this one will give us. We have our I1 to be equal to uh, total current, which is IT, equal multiplied by R2 over R1 plus R2. So please, I'm sorry for this squeezing I'm doing here. So I have to quickly reintroduce the demarcation. So, or if I should write it here, so from here we are going to have our I1, as I have quickly transferred it here, to be IT I1 equals to IT R2 over R1 plus R2. So similarly, we are still going to have our I2 in the other case. So our I2 is going to be the reverse of this. So our I2 is going to be definitely IT equals to R1 over R1 plus R2. So this are the value of the equation of to find a resistor, the current that flows through each resistor in a parallel circuit. So now let's say we have more than just two parallel circuits, like what we have here. We have more than two parallel, so we have 1, 2, 3, 4, 5, and so on and so forth. So now what we are going to have is going to be different from what we did here. So let's say from there, let's quickly recall our equation one, which says Ix equals E over Rx. So that is what our equation one says, and we replace our what they call it, our E with we have Ix equal to IT T over Rx. Sorry, Rx. Now, so let's take these things one after. Let's make use of this one after the other. We already know that we are going to substitute the value of what the total current. So let's say in this circuit now we have how many circuits? How many resistors? We have 1, 2, 3, 4, 5. So let's say we have 5 resistors branches that in a parallel circuit. Yeah. So we are going to find the current that flows through each of these resistor. So what do we do? The first thing we are going to look for is the total resistance. So our total resistance, which is our RT, so is going to be 1 over RT, which is equal to be 1 over R1 plus 1 over R2. So up to 1 over R5. So now with this, now we can find the current that flows through each of these parallel resistors. So now by substitution, just like what we did in two parallel resistors circuits. So we are going to substitute. Let's say we are looking for current that flows through the first resistor, which is R1. So it's definitely going to be from our initial equation, which is going to be what? IT uh, RT over R1, sorry. So which is definitely going to look like this. I1. So I1 equals to IT 1 over R1 plus 1 over R2, 1 over 3, over R2, R4 to R5, sorry. So over R1, and the same thing is applicable to I2. So that is IT multiplied by the equivalent resistance over R2, and the same thing is applicable to, so everything up to I5. This is how you are going to do for each. So which is also what I5 equal to IT multiplied by the total resistance. So all over R5. So and finally, before we go, let's quickly take a look at this question here. We say, for the network below, determine the current I1, I2, and I3. So the first thing we must take note is uh, our total resistance. So we must, it is very, very important that we look at our total resistance for first. So our total resistance, as we know, sorry, this is 1 over RT. Sorry for that. It's going to be R. So we have more than two resistors here. We are going to apply 1 over R1 plus 1 over R2 plus 1 over R3. So by the time we apply, so our R1 is 1, 2, and 4. By the time we apply all these things or substitute all these value into our equation here, so we are going to have uh, 1 over RT equals 1 over 1 plus 1 over 2 plus 1 over 4. So by finding the LCM, we should have 1 over RT equals to, so sorry, this is 1 over RT as well. We have not changed anything. 1 over RT is equal to 1.75. So by the time we take reciprocal of this now, definitely our RT will finally give us something around 0.571 ohm. Sorry, 71 ohm. So that is really the value of our RT. So now with this, to calculate our I1 now, so we are just going to recall our former equation, which is our formula. So we are going to say our I1 uh, equals to the total current that flows to it multiplied by total resistance over the value of the unknown current, resistance of unknown current, which is R2. So from there, we can take it further to by substituting all our value into this equation. We're going to have our I1 equals to total current that enters the circuit is 14 ampere. So 14 ampere into total resistance, which is 0.571. Everything over R2. The value of the R2, which is, sorry, R1, I think is R1. That is what we are looking for. The value of the R1 is 1. So if we punch our calculator, we should have our I1, and which is the current that flows to this first resistor, to be 8 uh, ampere. So I think we can try that, or approximately 8 ampere. So my calculator was giving me 7.99. I think that is approximately 8 ampere. So um, the same is applicable to I2. So if we are going to do our I2, we are going to have I2 equals to uh, I total as well, multiplied by the equivalent resistor resistance over what, over R2. So by the time we do our substitution, we are going to have 14 multiplied by what, and 0.571 over the value, which is 2. So value of I2 is going to be um, so 2 cancel, and that is going to remain 7. So 7 times this. So let's quickly punch our calculator. So I think we are having approximately 4 ampere. So we are having 4 ampere. So now we should try for the third one, or we should do it together. So our I3 on the other hand is going to give us the same thing by repeating the formula IT RT over uh, R3. So we're going to have 14 into 0.571 over R3, which is equal to 4. So everything altogether, our I3 altogether, by punching our calculator, we should have I think approximately 2 ampere. So 2 ampere. So I think that's all on the current that flows through each resistor in a parallel circuit that we have here. So, and again, we can also relate it to, let me just introduce this. We can also relate it to conductance. So we said that conductance is the inverse of resistance. So which is the inverse of RT. So since our RT is what, is 0. Which is going to be 1 over 0.571. So it's still going to give us what we have here. So the inverse of R2, which is our value of a conductor, is going to be 1.75, uh, uh, 1.75. That is the symbol of unit of conductance. So if we are going to apply this, so in terms of conductance, our higher one is going to give us G1, sorry, G1 over G total, which is multiplied by what? IT. So which is going to give us 1x divided by 1.75, multiplied by 14, so our I1 is going to still going to give us 8 ampere, so no matter what, which is approximately 8 ampere. So if we calculate for I2 as well using our conductance, we're going to have IT. So instead of R, we are using what? So we will notice something like this, as we said that what conductance is the inverse of a resistance. So if you look at our formula here, we notice our what do you call it? Our total resistance is up. So in this case, our total resistance is going to be down. So and the value of the conductance of the value of the particular resistor we are looking for will be at the top. So it will be the inverse of this. That is why we are having our G2 to be at the top instead of R1, instead of R2. So we have GT to be at the bottom. So by the time we substitute it, we are going to have 14 into what? G2, which is 2 over G total, which is what? 1.75. So everything, so our I2 is going to be approximately what we have here. So it's still going to be the same thing, which is what do we get in the end? So I think it's 4 ampere. So that is what we're going to get. So the same thing if you're applicable for I3 as well, we can test it on our own. I think we should have approximately 2 ampere as well. So that's to check the correctness in relation to conductance. So on that note, we are going to stop on CDR, which is current divider rule. So you are feel free to post any question that is troubling you based on this topic. So you can also refer to our former topics on this series, which is understandable electric circuit. So thank you as you follow us in this series. See you in the next class. Bye bye.